Another way to represent the power is through a complex power. And this type of power, this can be considered as a type of power. And it is composed of two components, just like in the impedance, which is also be represented in a complex number. And also, this is significant, especially in power analysis, because through this complex power, we can determine some information regarding the power that is being absorbed by a given load. So now, let us look at if we have a voltage source V, and this voltage source V has a magnitude, let's say this is RMS, and this is in complex form because we're talking about the complex power now. VRMS, this is the magnitude of V, or I can just write here. So I will change my notation now. Later on in the next discussion, when you see a capital letter V here, this means this is a complex quantity. If I wrote just like this one, absolute value, it means the magnitude of that V. So if this is the RMS value, and this is the magnitude of that RMS value, and it has an angle theta, let's call it theta V. And also we have the current, the RMS current, the magnitude of that with the angle of theta I. Now, I want to determine the complex power because these are complex voltage and current, so I just need to multiply the two. So the complex power is actually the apparent power. This is the complex number version of the apparent power, S. And this will be equal to the product of the two. But this time, because we are multiplying these two, remember the concept of complex. When we multiply them, we add the angles between this complex number in polar form. So now if we add them, the resulting angle now for S will be the sum of the two, which is not a good intuition because we know that the angle of that S should be the power factor angle, which is should be the difference of these two. So what we do is, instead of multiplying them directly, we multiply the voltage with the current, and this time it should be, this asterisk here means this should be the conjugate of I. This should be a conjugate, meaning we just need to change the sign of the angle of this one, theta, I, into the negative, or the conjugate. So if we multiply now, so S, we have the magnitude of V times the magnitude of I. Then we add the angles, because this is a conjugate, so this should be theta V minus theta I. And we actually know this. This is just, if we let theta, the power factor angle, which is just the difference between the phase angle of the voltage and the current. So our S now will be equal to the RMS magnitude of the voltage in the current with the angle of theta. This is in polar form. So this is a complex power. Now, and the unit here is still in volt ampere. But now, if we want to convert this, because we want to convert not in we want it to be in rectangular also, so that we can determine some information about S. Just like the impedance, if you remember, impedance Z is equal to R plus or minus JX. So if it's in rectangular form, we can determine R and we can determine X. Here, it's the same thing. It's similar. So we want to determine the components of this S in polar form. So how do we do that? We can use S will be equal to what? This product, V times I, multiplied by the cosine of the angle, cosine theta, then plus or minus It's plus or minus. Let's make it plus or minus j. Then also this time, this should be v times I multiplied by the sine of the angle theta. So this is the conversion. If you remember r theta, we convert this one into rectangular form. This is r cosine theta plus j sine theta, or this is the shortcut for this is the one that we use sees. R sees theta. This is the same as r angle theta. So, but here, if you look at this one, this is somewhat familiar. The product of the voltage, RMS current multiplied by cosine theta. What is cosine theta? This is the power factor. This is actually the real power. And also, this one, the sine theta, this is the reactive power factor. You multiply it with the product of the voltage and the current, the apparent power. This is just equal to Q. So in general, now, our S, the complex power in rectangular form, will be just equal to the real power plus or minus J Q. And if you solve this one, the real power, you have the real power and the reactive power, then apparent power. So from here, you can determine the actual apparent power by converting this again into the polar form here. Or just take p squared plus q squared, the square root, because this is a rectangular. If you convert it into polar form, you just take the square root. It's the same formula as in the power triangle before. So you don't need to memorize the power triangle anymore. If you know how to convert polar form into rectangular form, so you know how to add complex numbers in the different forms. So this is special because if we solve the total power, remember the power is independent with the connection. We always add them. So if we consider them into the complex form, we can just add them all, then we can solve for the total power. And from that, if you can solve for the total complex power, then it means it will give you also the total real power and the total reactive power and apparent power if you know the complex power. So this is very significant. So this means if you know now the complex power, if you want to determine the real power here, you just take the real component of that apparent or the complex power. For the reactive power, you take the imaginary component of this complex power. And the relationship between the impedance also, if you remember, if you want to solve for the impedance Z is just equal to the voltage all over I. So here I wrote them in bold letters. This means they're all in complex numbers. So we have an angle. The angle of the impedance is actually the power factor angle theta here. So now if we go back to our definition of S, here the voltage times the conjugate of I, and if I solve for I from here, or we can solve for V instead of I, V will be equal to I times Z here. Then I will substitute this value for V in S, so that we have S is equal to V, which is I, times Z, multiplied by the conjugate of I. Now remember, I has an angle here of theta I. But here, because this is a conjugate, this is negative theta I. So if you multiply them, theta I, we just add the angles, the phase angles. So theta I plus negative theta I will become 0. So the formula now, we can also rewrite this one. The phase angle will be 0. So we can just say that the magnitude of I, you square that because this is I times I. We don't have any angle anymore because it will be equal to 0. Then you multiply it with the impedance Z. And it's true because we know that the angle of Z is theta. And therefore, the total angle also of S is still angle theta from here. So this is another formula. If you know the RMS value RMS value of the current, you square that and you multiply it with the total impedance of the load, the complex impedance of the load, then you will find the complex power. But for the voltage, instead of current, so if I substitute the voltage, so if the current is equal to here, voltage all over Z, I substitute this one into this equation here, V times I, because I here is a conjugate. So what we do here to make this one conjugate is we just make Z also a conjugate complex number. So our S now will be the magnitude of V squared all over the conjugate of Z. So it's not just all over Z, but you should divide it with the conjugate of Z. Unlike the current, you need to multiply the actual Z. So conjugate here, you need to make the complex part or the imaginary part a negative or the opposite sign. And also we can determine, because we know I now is equal to, this is just a constant I. Z, we know Z is equal to R plus JX, or plus or minus JX. Now, if we substitute this in our equation here, S will be equal to I, the magnitude of I, squared multiplied by Z, which is R, plus or minus JX. Then, because this is just a number, we can distribute that directly, and we will be having I squared times R plus or minus JI squared times X. And you look at this, again, this is in polar form. This is our real power, and this is our reactive power. So we can conclude that the real power is due to the resistance or resistor, while the reactive power is due to X. So here we can say that I is just equal to I squared times R. These are all magnitude, because this is not a complex, and Q is I squared times X. So we can use this formula later on when you want to solve for the real power absorbed by the impedance or the load, and also the reactive power that being absorbed and given by the load. So from this, we can say that the complex power is really very useful for us to identify or determine this different information based from this formula here, S equals P plus JQ.